Hello everyone. We are ready to start Chapter 6. In Chapter 6, we will define what is meant by a production function. We will later on use the production function and combine it with the costs of our inputs to solve the cost minimization problem of firms. And before we begin, let's take a look at the overview of the course. In the first half of the course, we discussed consumer theory and we solved the utility maximization problem of consumers. From that, we derive the consumer's demand curve, and we can aggregate the demand curve into a market demand curve. Moving forward, we will first define and solve firm's problem, which is a cost minimization problem. We are answering the question that given the prices of the inputs and given the technology or the production function of the firm, if the firm wants to produce a certain level of output, what is the minimum amount of cost the firm has to incur or the firm has to pay? From that, we can combine both the demand from the consumers and how the firm can provide the goods to solve the profit maximization problem for firms. There are different market structures. In this course, we will mostly focus on the first one, which is perfectly competitive market. In a perfectly competitive market, from our solution to the firm's cost minimization problem, we can derive the supply curve for the firm. Combining it with the market demand curve we find from the individuals, we can find the short-run market equilibrium. In Chapter 11, we have a different market structure, the monopoly market. And in that market, there is we do not derive supply curves for the firms, and we will solve the profit maximization problem for a firm in a different way, and we will see when we come to that. And this is the overview of today's presentation. So we are going to first define production function, and I'm going to first introduce what is meant by production and what is meant by the technology of the firm. The production function will be a function, a mathematical representation of the firm's technology. And you will realize that production function is to some extent similar to the utility function that we have discussed previously. We will similarly define the marginal products of labor and capital. So the labor and capital here are the inputs of the firms. And we will define what is meant by isoquant, the marginal rate of technical substitution between the inputs for the firms. We will describe the three special types of production functions. And eventually we will introduce a new concept, which is return to scale. So ever since long before, human beings are involved in production behaviors. So production is a behavior that involves transforming some type of resources into other type of resources. And we call the first resources inputs and the second outputs. So inputs are mostly labor, raw materials like minerals, and sometimes services provided by intermediate goods, or such as land and machine. Outputs are usually the goods that we can consume. For example, food, clothing, or entertainment. And of course, outputs can also be sometimes intermediate good, such that other firms will use it as inputs. If we think of the production of a smartphone, an iPhone, for example, it is not completed by a single company, but there is a chain of production from the very raw material to eventually an iPhone that a consumer to eventually an iPhone in a consumer's hand. There are many intermediate goods that are being produced and eventually assembled. So in ancient times, the most Oh, the oldest production behavior is that people go out and hunt for food. In this case, people are transforming their time or their human power into food through production, and the production behavior is hunting. And if we look at the factory in nowadays, the factory is using all different types of complex machines, as well as hiring workers. So by combining workers, machines, machine powers, and also many different kinds of raw materials, the factories are producing all kinds of high technology goods that we use in our daily life. And the process of production does not necessarily mean that we can see the final output. For example, if you go to a concert, the performers are producing services, which is entertainment, and that kind of entertainment makes you happy, brings you satisfaction, brings you utility, and the audience are consuming the production of the performers, right? So in that case, it is also a process of production. And if you recall what you learned in macro class, if you had taken it before, when we calculate the GDP, the gross domestic product, we were saying that we were adding up the market value of all the final goods and services produced within the country. So it's not only the goods that we can see, like food and clothing and cars and phones, but services such as if you get a haircut in a barber shop, um, the barberman is producing. If you go to a concert, performers are producing. If you listen to music, it's also being produced by the singers, etc. All those process are production process. So the term technology we use in economics describes how effective or the ability that the firms have in transforming those resources. So from the two graphs, both are the textile industry or textile manufacturing at different times. If we think of textile manufacturing before the Industrial Revolution, it is very inefficient and it uses a lot of human power or labor hours. But nowadays, we have those large factories. Many processes are automated, and we have the machines to help us produce clothes. And similarly, if we think about growing crops before industrialization and after, uh, I would say that the majority of humans' labor hours or human power were devoted to farming, to growing crops, or to basically grow enough food to feed ourselves before industrialization. But nowadays, with the help of technology improvement, with the help of machines, we do not need as much people to grow crops, and we can have people. So people can start working in factories. People can start working in financial sectors or education sectors, so that we have more and more other types of good, including entertainment, that are being produced and enjoyed by um, everyone, basically. So those technology improvements not only allow a single firm to produce more goods, but overall it allows the society to produce more goods with the limited resources that we have. And the very first limitation is the human power that we have. And improvements in technology allows us to produce more goods with those limited resources. So over the history, the technological advancements are improving people's standard of living. And well, the concept of technology is somewhat abstract. So to be able to analyze it, we are going to use mathematical representation to represent the technology that the firm has. So we are going to use this production function that tells us the maximum amount of output that the firm can produce for certain level of inputs. And if we think firm uses labor and capital, we usually use L, that stands for labor, and K, that stands for capital. So we can write Q equals to F as a function of labor and capital to represent the technology that the firm has using labor and capital to produce the output. And here Q is the quantity of the output. And this is the case that the firm uses two inputs. The firm can use only one input, or more realistically, more than two inputs. So if the firm has a production function with a single input, let's say labor is the only input, then the production function will be a function of labor. And for example, let's say Q equals to L. Then basically this says that employing L units of labor will allow the firm to produce a maximum L units of output. And I forgot to mention in the previous slide, here we have a term maximum because it is possible that the firm is not producing at this maximum level, right? So for example, if the firm has poor management within it, it may not be able to fully utilize the technology that it has, and some of the labor power it hires will be wasted due to poor management. But as economists, we are not, at least in this part, we are not especially interested in the management within the firm. So we are going to focus on what is the maximum possible output the firm can produce with its technology. And given this production function, each unit of labor can produce exactly 1 unit of output. And this is a very simplest case. We can think of this as, say, a human being making, well, we can think of this as a craftsmanship, for example. So every hour, this person makes some small widgets, and it's kind of a steady production process. And for different production functions, we want to understand, or we want to describe how productive the production process is, or how productive the technology is. We're going to introduce two concepts. The first one is average product of input, and in our case, average product of labor. This is basically dividing the total quantity that is produced by the amount of labor the firm uses. This tells us how much each unit of labor, well, on average, how much each unit of labor is producing. The second concept is marginal product of labor, or the marginal return of labor. This is similar to the concept of marginal utility. This is the additional output the firm can produce by increasing labor by 1 unit. And we are going to differentiate our total production function with respect to labor. And this is similar to the concept of marginal utility, and graphically, if you recall, marginal utility is the slope of the utility function. And here, this marginal product of labor is going to be the slope of our production function when we have a single input. This is an exercise from the textbook, problem 6.7 in the textbook. And I just want to go through this problem with you all so that we make sure everyone is clear about those two concepts. And let me write down on the top what is our APL and what is our MPL. So the APL, the average product of labor, is our total production divided by the unit of labor we employ. Our MPL is going to be differentiating our total production with respect to labor. And well, that is a continuous case. Here we have a discrete case. And by discrete, we are looking at units of labor increase one by one, right? And if we recall the concept of marginal product of labor, it is telling us what is the increase in the output the firm can produce by employing an additional unit of labor. So the MPL can also be written as the difference in the total output the firm can produce by using L units of labor and the total output the firm can produce by employing L minus 1 units of labor. This difference is exactly the additional output the firm can produce by employing the Lth unit of labor. And let me put it down here. This difference is the increase in output by employing the Lth unit of labor, which is exactly what MPL is saying. So we use this formula in the discrete case. And we have a whole bunch of empty cells. Let's start from the top to bottom. So the first cell I will try to fill in is the one on the third row. To fill in this cell, we can directly apply the formula of APL. APL is the total quantity or the total output divided by L. And we are given that we are producing 19 units in total by employing 1 unit of labor. So therefore, the average product of labor is 19 when we employ 1 unit of labor. Now let's move on to the fourth row when we employ 2 units of labor. So because APL equals to Q divided by L, we can multiply L by 2. We can multiply both sides by L. We will find that APL times L equals to Q. And in this case, APL is 36 and L equals to 2, so that we can calculate our total output is 72 units. We can then fill in the cell in the last column in the fourth row. So we are going to use the second formula, MPL, and the marginal product of labor, or the marginal product of the second unit of labor, is the difference between the total output in the second unit and it's going to be the difference of the total output by employing 2 units of labor and the total output by employing 1 unit of labor. This difference, based on the numbers that we have calculated, is 72 minus 19, that is 53. So the marginal product of the second unit of labor is 53. All right, now if we look at the fifth row, all 3 cells are empty. We can start from the total product by using information we have on the fourth row. We can rewrite our equation a little bit. So since the MPL, and let me emphasize here, the marginal product of the we are going to actually use information from the row below it, which is the information in the 6th row. So the marginal product of the 4th unit of labor is going to be the total output we can produce by employing 4 units of labor minus the total output we can produce by employing 3 units of labor, right? We are using the second formula again. And if we rearrange this formula, we can see that the total output we can produce by employing 3 units of labor is the difference between Q4 and MPL4. And we can actually find both Q4 and MPL4 in the following row. And let me make this, how do I make this smaller? Okay, we can find both of them in the following row. So we can calculate Q3 by subtracting MPL4 from Q4, which is subtracting 256 from, or which is subtracting 103 from 256. This is equal to 153. So our Q3 equals to 153. All right. Let me just underline it. Q3 is 153. Here I didn't write, but I should have written, which is our Q2 equals to 72. And also here I didn't write, but I should have written, this is the marginal product of the 7 units of labor. So it is the MPL2, and this equals to 53. And also here, this is the average product. So all the APL and the MPL are functions of the units of labor that we employ. All right, so this Q3 equals to 153 is a little bit tricky, but we also solved it. Now with this, we can easily calculate our APL 3, and this is Q3 divided by 3. So it is 153 divided by 3, which equals to 51. And the MPL, the marginal product of the 3rd units of labor, is Q3 minus Q2. And in this case, it is 153 minus 72, which equals to 81. Now we have actually used all the techniques that we needed to solve this table. So from now on, I will go a little bit faster, all right? So here, the average product of labor when we employ 5 units of labor is Q5 divided by 5. That is 375 divided by 5. And this equals to 75. The MPL is, well, Q5 minus Q4, which is 375 minus 256, and this is 119. So this cell, the total product of the, when we use 6 units of labor, is slightly different. And here we are going to use the, again, use the second equation, because when we are missing both the total and the average, we must use the marginal to derive it. And we can see that the MPL Q6 is Q6 minus Q5, right? This would imply that Q6 equals to MPL 6 plus Q5. And we have both of those two information. So Q6 will be 375 plus 129. And this equals to 504 if my math is correct. And with this, we can calculate the APL 6. This is going to be Q6 divided by 6, and it's 504 divided by 6, and this is going to be 84. All right. So actually, I think up to this point, we have used all different kinds of tricks that we could use to fill in those blanks. So I will not go through all the remainings to save time for this recording. I don't want to make this recording too long and kind of force you to watch all the remaining math. You should practice on your own, and if you are unable to fill in some of the cells, just try to manipulate with those two equations, especially the second one. You can see that we can kind of move one expression to the other side and etc. to see if we to see how you can use the existing information, if the information you already have, to calculate the ones that are missing. And if you have a problem, ask me in the office hour, or ask Jasmine in her office hour or the discussion, and I will just stop here to do not spend too much time on this question. And here, let's so in the previous we did an example when the production function is given in a table. So in this slide, I'm going to draw the APL and the MPL on the graph when we have a continuous production function. So let's say our production function of a single input labor is Q equals to the square root of L. So what to draw this production function on a graph, we are going to put units of labor on the horizontal axis and the units of output we can produce on the vertical axis. And we have drawn this in the utility function case, like U equals to the square root of X, right? They are going to be of exactly the same shape. And if you recall, so you can kind of substitute in a few values of L to plot it. You can also use a graphic calculator or help from online tools to see how we can draw the graph of Q equals to the square root of L. So I would know its shape is going to look something like this. It is going to be a concave curve that is upward sloping but becomes flatter and flatter as L increases. All right. So we were saying that APL equals to Q divided by L. MPL equals to the derivative, which is also the slope of the curve. So how can we reflect those two on this graph? So let's just pick a point here. Let's look at this point A over here. So at this point A, we are employing L units of labor, and we are producing Q units of output. And APL by definition is the ratio that is Q divided by L. On this graph, it is reflected to be the slope of this line segment, this red line. So the slope of this red line is exactly Q divided by L, which is our average product of labor. All right, and if we say, look at a slightly different point, that is, for example, here, then similarly, if we connect this point B with our origin, so this is our point B. If we connect our point B with the origin, the slope of this orange line segment is the average product of labor at point B. So the slope of the red line is the APL at point A. And I probably should have put it here. So for every point on this graph, we can connect it with the origin and find the APL, which is the slope of this line segment. And it is Q divided by L. We can see that as L increases, this line segment becomes flatter and flatter. So the slope of it becomes smaller and smaller. For this production function, as we employ more units of labor, the average products of labor are decreasing. All right. Now, if we go back to point A, and if we want to find the marginal products of labor at point A, and as we know, the derivative of a curve is the slope of the tangent line to the curve, or it is the slope of the curve, basically. So at point A, let's say this green line is tangent to our production function at point A. Then the marginal products of labor at point A is the slope of our green line. So the slope of green line is the marginal products of labor at point A. We can see that given this production function, the slope of the green line is smaller than the slope of the red line, right? Green line is flatter, the red line is steeper. So the marginal product of labor at point A is smaller than the average product of labor at point A. This actually also holds true at point B. So at point B, if let's say this pink line is tangent to our production function at point B, then the slope of the pink line is the marginal product of labor at point B. And this tangent line is also flatter than the orange line. The marginal product of labor at point B is also smaller than the average product of labor at point B. And of course, those conclusions are like special to this production function. If you have a different production function, you may or may not get this conclusion, all right? But on this graph, we can draw those conclusions. And this is how we can plot the APL and the MPL on a single graph. So the production function with a single input can give us some sense of how production functions look like, but they are not especially interesting. And for our analysis, or for the question that we are going to solve, we are mostly focused on production functions that has two inputs. For the same reason as what we did in the consumer theory, with two inputs or with two goods, we can study the consumer or the producer's trade-off between using those two goods. And the trade-off can be similarly extended to more than two goods. So if we have 3 goods, 4 goods, 5 goods, and even more, it is going to be more abstract to imagine what is going on, but essentially or mathematically, the consumer is making trade-off between different goods, and he's finding a point at which he can no longer improve herself, either in the sense of improving her utility or improving her level of satisfaction, or in the sense of reducing her cost in production. All right. So the two inputs is the simplest case that we can have to unravel this trade-off between different inputs or different goods. So if the producer has a production function of 2 goods, we write Q equals to F parentheses L comma K, and we can have different kinds of production functions. And for example, if the production function is Q equals to the square root of L times K, this is saying that when the producer or when the firm employs 2 units of labor and 2 units of capital, we can substitute those values into our production function. And we will realize that Q equals to the square root of 2 times 2, which is the square root of 4, which is 2. So this is saying that by using 2 units of labor and 2 units of capital, the firm can produce at most 2 units of output. And here we have at most or at maximum because the firm may not actually produce at its efficient level. And similarly, if the firm employs still 2 units of labor but 8 units of capital, we can substitute those values into our production function, and we will realize that Q equals to 4. So this is saying that by employing 2 units of labor and 8 units of capital, the firm can produce at most 4 units of output. And for all different combinations of L and K that we substitute into our production function, we can calculate the value of Q, that is the maximum units of output the firm can produce with this production function by employing the given combination of labor and capital. Now, given the production function with 2 inputs, we are going to define a new concept, which is the marginal product of labor or capital with 2 inputs. Similar to the consumer theory, if you recall the marginal utility of a good when we have 2 goods, here the marginal product of 1 input when we have 2 inputs is the additional output that the firm can produce by increasing one input by 1 unit while holding the other input constant. Very similar to the marginal utility when we have 2 goods. And everything the same, mathematically, we are taking partial derivatives of the production function, of the total production function, all right? And I put it here that this is totally an analogy to the marginal utilities. And we also have a similar law, that is the law of diminishing marginal product. It says that the marginal product of labor or capital is decreasing as the firm uses more labor or more capital. And again, I want to say that this is not always true. So let's imagine that we are increasing the number of software engineers in a team. So for the first software engineer that we hire in the team, well, he or she can produce some output, but assuming that we hire a new software engineer, then not only can they program at a faster speed, but they may be able to brainstorm together as a team and either program in a more efficient way or come up with different kinds of solutions that to program faster, for example. And if we employ a third software engineer, they might be improved on this end even better. So the first few software engineers we employ are going to have an increasing marginal product, right, of labor in this case. However, as the number of software engineers we have in a team increases and goes beyond a certain threshold or a certain number, we are having too many software engineers in a team, and this could start to make coordination a very difficult task. And in this case, by hiring even more software engineers, the benefit that we obtain from brainstorming is going to decay, but the cost, which is the coordination problem, will become more and more important. And here, the marginal product of labor, or the marginal product of an additional unit of software engineers, is going to be diminishing. So over different regions, this law may or may not hold. And in the textbook, figure 6.2 did a quite good job showing you how this looks like on the graph. So we are going to focus our analysis on the region where this is true. So we are going to focus, if we were analyzing software engineers, we are not going to focus on the first few, but we are going to imagine that the firm has already hired quite a few software engineers, and we are looking at the point where hiring more software engineers are having a decreasing or diminishing marginal product, all right? After, so this is another concept that we can find an analogy in the consumer's theory. So the isoquant, I'm not sure if this is a new word to you. So the way I understand this word is it has two parts, iso and quant. Iso means like the same, and quant refers to quantity. So isoquant is something that is giving us the same quantity, all right? And the definition of it is that it is a curve consisting of all the combinations of labors and capitals that we can employ. And all those combinations of labor and capital are going to produce the same level of output, the same quantity. And you might have already thought this is a very similar concept to the indifference curve that we had. And recall the indifference curve is the combinations of good X and good Y that will give the person the same level of utility, right? So here, the isoquant is the combination of labor and capital that will produce the same level of output. So if we were to look at an example, let's say we have a production function that is Q equals to the square root of L times K, same as before. Then all combinations of L and K such that Q equals to 20, or that the square root of L times K equals to 20, or that L times K equals to 400. All such L and K are going to be on the same isoquant because all those combinations are producing 20 units of output. And the same as the indifference curves, we can draw infinitely many isoquants on the graph, and none of those isoquants will intersect each other for the same reason that indifference curves do not intersect each other. And now let's look at another problem in the textbook, 6.8. So we are given a table that tells us how many units of labor we use in the columns and how many units of capital we use in the rows. And each cell tells us the total output that the firm can produce. So basically, this is a production function, but presented in table. We want to draw a graph and showing some of the isoquants on this graph. So let's draw the graph first. So usually we are going to put labor on the horizontal axis and capital on the vertical axis. So let's mark some points over here. When the firm uses 0 units of labor and 0 units of capital, the firm is producing nothing, which is the origin point. When the firm uses 1 unit of labor and 0 units of capital, that is this cell. So 1 unit of labor and 0 units of capital, that is here at this point. The firm is producing 2 units of output. So this is 1 unit of labor. And let me always use the, let me always use the green color to indicate the amount of output that this point produces, all right? So in this case, the firm is producing 2 units of the output. Now, if the firm uses 2 units of labor and 0 units of capital, that is this point, 2 units of labor, the firm produces 4 units of output. So similarly, if the firm uses 3 units of labor, the firm produces 6 units of output and 0 units of capital, of course. And let me do the rest in a pretty fast way. We are basically translating everything that is on the table to our graph. And recall, the black is the units of labor and the unit of capital that the firm uses, while the green one is the total output that the firm is producing. So we are basically looking at this 5 by 5 grid line or grid. So we have the amount of output the firm produces at each of those points. We have 25 points. So this is also 2 units. This is 4 units at this point, 6 units at this point, and 8 units at this point. So it is 4 units here, 6 units here, 8 units here, and 10 units here. So I forgot to put 8 units at this point. So this is 6, this is 8, this is 10, this is 12. And this is 8, this is 10, this is 12, this point is 14. It's a not well drawn point. This is 10, this is 12, this is 14, and this is 16. So I've put everything in the table onto the graph. A black point is the combination of input it uses, and the number in green is the total output it produces. We can combine or we can connect some of those points to draw the isoquant. So these 2 points, and let me use the red line to represent isoquant here. So those 2 points are both producing 2 units of the output. And recall the definition of isoquant. It is the combination of all the inputs that produce the same level of output, right? So those 2 points are both producing 2 units, so they must be on the same isoquant. Similarly, those points are all producing 4 units of output, so they must be on the same isoquant. Now, if we connect the points that produce 6 units, the points that produce 8 units, the points that produces 10 units, the points that produces 12 units, that produce 14 units, and we have only one point that produces 16 units. And well, my drawing isn't well, but they should actually be straight lines. So we can use Q equals to 2 to represent this first isoquant. Q equals to 4, this second one. Q equals to 6. Q equals to 8. Q equals to 10. Q equals to 12. Oops, this one is Q equals to 12. And lastly, Q equals to 14. So it's tempting to extend those lines, but just given based on the information we were given in the table, we couldn't really do that. So we can draw a whole bunch of isoquants on this graph by representing what we see in this table. All right. And let me clear the drawings. So next we want to find the marginal products of capital and labor for each pair of inputs in the table. And let's go back, recall the definition of marginal products of labor and capital when we have 2 inputs. It is the additional production in labor holding the, so it is the additional amount of output we can produce by increasing labor by 1 unit, holding capital constant. This is the marginal product of labor. The marginal product of capital is the additional output we can produce by increasing capital by 1 unit, holding labor constant. So to do this, we can say that the marginal product of labor, of the third unit of labor, for example, so let's be more precise here, the third unit of labor hold capital constant, and say let's hold capital at 1 unit. All right. So this is, by our definition, is the total quantity we can produce by employing 3 units of labor and 1 unit of capital, subtracted by the total quantity we can produce by using only 2 units of labor and 1 unit of capital, right? So we are holding capital constant at 1 unit. We are looking at the marginal product of the third unit of labor. So we are looking at this expression. And if we look at the table, when L equals to 3, K equals to 1, this is 8. And when L equals to 2, K equals to 1, this is 6. So the marginal product of the third unit of labor holding capital constant at 1 unit is 2. And let me write down this sentence. Marginal product of labor of the third unit of labor holding capital constant at 1 is 2 units. All right. This is what this calculation tells us. So we can, let me do another one. Let's look at the marginal product of capital, for example. So let's say if we want to look at the marginal product of capital, and let's say I'm interested in the second unit of capital, so K equals to 2. And I'm going to hold labor constant. So let's say we hold labor constant at 4. For this is going to be the quantity we can produce by employing 2 units of capital and 4 units of labor. We subtract from it the output we can produce by employing 1 unit of capital and also 4 units of labor. So let me actually put it here. And we can look at our table. When L equals to 2 and K equals to 4, this is 12. Sorry, when K equals to 2 and L equals to 4, this is 12, yes. And when K equals to 1, L equals to 4, this is 10. So this difference is also 2 units. And what this is saying is that the MPK of the second unit of capital holding L constant at 4 is 2, all right? And you can do this exercise for every single cell in the table. And you will realize actually all of those are 2 for the numbers that's given, and it's given purposefully, I think. But just to practice or to demonstrate how we can answer this question, well, this is the process that we go through to find the marginal products for each pair of the inputs in the table. All right, now we are looking at another very familiar concept, or a concept that is analogous to the concepts we learned in consumer theory. So here we call this the marginal rate of technical substitution, and in consumer theory we called it the marginal rate of substitution. So by employing the term technical, this is reflecting the substitution of technology between the groups. So the marginal rate of technical substitution of labor for capital, if we use the subscript L, K when L comes first, is the rate at which we can substitute our labor with capital, basically. So it is the quantity that the capital can be reduced for each unit increase in the labor that we employ. Or we can say that this is the rate at which we need to increase capital if we were to decrease our use of labor by 1 unit. And most importantly, we are holding the quantity of the total output constant. And in the consumer theory, we are substituting between the 2 goods and holding the utility constant. Here we are holding the total quantity of output constant, and we are looking at how we can substitute between the 2 inputs, all right? So on the graph, the marginal rate of technical substitution is going to be the slope of the isoquant. And how we calculate it is also analogous to what we did in the consumer theory. It is the negative of the ratio of the marginal product of labor to the marginal product of capital. So I'm going to draw a graph that you have seen many times before. And recall the isoquant we draw in the two slides ago, they were straight lines, I was saying, right? Because of the numbers given in the table. But more generally, the isoquants are going to, well, look like the indifference curves in shape, at least. So those will be the isoquants. And the marginal rate of technical substitution, as we were saying, are slope of those isoquants. So the MRTS, so I should have typed first. We usually put labor on the horizontal axis and capital on the vertical axis, all right? So the MRTS are going to be the slope of those indifference curves. So let me highlight here, if this is point A, so we can say that the MRTS at point A is the slope of the red line. And if we were given the production function, we can calculate both the marginal product of labor and the marginal product of capital. We can substitute the value or the coordinates at point A into the expression, and we can calculate it. And the process of calculation is, again, very similar as the one you did for calculating the marginal rate of substitution. It is just that here it is a new concept. It is the marginal rate of technical substitution, all right? So for the isoquant, those are the isoquants, and we can say that this is Q equals to Q1. So every point on this isoquant, the firm is going to produce, if the firm employs this combination, a combination of inputs that is on the isoquant, the firm is going to produce Q1 units of output. We can have another isoquant, Q equals to Q2, and Q2 is going to be larger than Q1, right? Because we are employing more inputs, basically, and we are likely going to be producing more output. All right, and here I'm just drawing everything in an abstract way because I don't have a equation for the production function. So generally, the isoquant might look like this. And if you have the equation for it, you can draw more precisely what it looks like. And you can calculate using equations the MRTS as well. All right. And this is, I believe, the last concept that is very similar to what you saw in consumer theory. So in consumer theory, we have the law of diminishing marginal rate of substitution. And here we have this law of diminishing marginal rate of technical substitution. And basically it states that the MRTS becomes smaller in absolute value as the number of labor that the firm hires increases. And this also has a very intuitive understanding. So let's hold the total output that we want to produce the same. So we are looking at points that are on the same isoquant. And imagine if the firm have hired many workers relative to capital per se, then it will be easier for the firm to substitute workers away with machines, right? And maintaining the same level of output. It would require less machine or less capital to do so. But if the firm has only hired very few workers, and the firm is trying to substitute workers with machines, it would require the firm to probably employ more machines. And by more, it is comparing to the first case. It would require the firm to employ more machines to substitute away one worker when the firm have only hired very few workers. And again, maintaining the level of output the same. So therefore, the MRTS is becoming smaller when the firm has hired more workers. And we can apply this same argument to our saying that when we substitute machines with workers, there will be diminishing MRTS. And let me emphasize here, this is the MRTS. And because it is substituting workers for machines, so it is L comma K coming here, right? All right. So if we were to apply the same arguments, we are actually looking at the MRTS of K comma L when K comes first. And this expression is also going to be different. It is going to be the negative of MPK divided by MPL. So this becomes smaller in absolute value when K becomes larger, all right? We are also going to focus on 3 special types of production functions, and those are our old friends. So we have the first, the Cobb-Douglas production function. And its general form is Q equals to A times L to the power of alpha times K to the power of beta. And note that when we were talking about consumer theory, we didn't have the constant A in front of our utility function, or the Cobb-Douglas utility function. Here, the constant A actually makes the difference, because in the production function, we are concerned about the actual quantity that is produced. In the utility function, we were only concerned about the relative ranking of different consumption bundles. And we can imagine that if we multiply our utility function by a positive constant A, then the relative ranking before the different consumption bundles are not going to be different. So the utility function is representing essentially the same preference. However, here, if we multiply A, we are actually saying that the firm will be able to produce A times more goods using the same level of inputs. And this is an important difference. And in some cases, we can use this constant A to reflect technology progress. And if there is a technology improvement, we can model that the constant A becomes larger so that the firms are going to be able to produce more outputs using the same level of inputs compared to before. And many of the properties of the Cobb-Douglas function, the production function here, we have derived it previously, including the marginal products of labor, the marginal products of capital. And in case you have forgotten, let me just write it down here. So given this general equation, the marginal product of labor is going to be A, which is a constant, times alpha, times labor to the power of alpha minus 1, then times K to the power of beta, because we are taking a partial derivative. So we are treating the capital as constant. We are differentiating with respect to our labor here. And the marginal product of capital is A times labor to the power of alpha. We are treating labor as a constant because we are taking a partial derivative with respect to capital. And for capital, we bring down our exponent, and we subtract 1 from our exponent. This is the formula we used to take partial derivatives. The second one is a linear production function or perfect substitutes. So in this production function, labor and capital can be perfectly substituted. by each other, we can think this as, for example, the production process can be either fully manually or fully automated. It's not in the form that it is human operating machines, but human can produce the good on his own, and the machine can produce the good on its own, possibly at a different level of efficiency, of course. But but the human labor hours can be perfectly substituted by the machines. The third production function is fixed proportion production function or perfect complement. So in this case, the amount of labor and the amount of capital must be employed at a fixed ratio to produce efficiently, and other employing labor and capital that is not at this fixed ratio is going to be wasting either some of the labor or some of the capitals. And an example is that, say, every machine has to be operated by 4 workers. So if you have more than 1 machine per 4 workers, or if you have more than 4 workers per machine, the additional ones are not going to be producing any more units of the good. In this case, the human power and the machines are perfect complements to each other, and it takes the form of Q equals to the minimum of A times L and B times K. And this slide, I'm going to introduce to you a new production function, a new function. It looks very complicated, and don't worry, I will not test any math or derivation based on this. All I want to do is to introduce you to this. So this is the constant elasticity of substitution production function. It takes this very complicated looking form. So here we have a parameter that is sigma, and this sigma is a positive parameter and represents the elasticity of substitution between our inputs, labor and capital. And in the textbook, figure 6.17 shows that actually the 3 different production functions that we saw just now, the linear production function, the Cobb-Douglas production function, and the fixed proportion production function are all special cases of this CES production function. Those 3 production functions correspond to 3 special cases or 3 special values that sigma takes. So when sigma is infinity, meaning that there is infinite elasticity of substitution between labor and capital, or to say that labor and capital are perfect substitutes, we end up with the linear production function. When sigma is 0, that is saying that there is 0 elasticity of substitution between the 2 inputs, or to say that the 2 inputs are totally not substitutable, right? So that means that we have to employ the inputs in a fixed proportion, and that gives us the fixed proportion production function. And the Cobb-Douglas is in between. It is corresponding to the case when the elasticity of substitution between the 2 inputs is 1. And when the elasticity of substitution between the 2 inputs takes other value, for example, 0.5 or 2, you can see the corresponding graphs on the textbook. And this is the last concept we want to introduce in this lecture, which is the return to scale. So this is a new concept. We didn't have this one in the consumer theory, because in the consumer theory, again, we are not really concerned about the absolute value of the utility, right? We are only concerned about the relative ranking of different bundles. So we can happily multiply it by a constant or etc. It doesn't make any difference. But here, the actual number or the actual number Q that the firm can produce is meaningful, and we are interested in knowing how this Q will change if we increase all of our inputs. So the return to scale is actually saying that if the firm operates at a larger scale, or if the firm scale up, and by scale up, we mean that if all the inputs of the firm increases by the same percentage, how much will this firm's output increase? So if the firm's, if all the inputs of the firm increases, basically the firm becomes larger, right? But is the larger firm going to be, so is a single larger firm going to be more efficient than several small firms, for example? Or is the reverse is true, that several small firms are going to be more efficient than a single larger firm? Those can be told from the return to scale concept, and we can derive this concept from the production function. So the question is, if the firm doubles all its inputs, do they also double the output they produce? Well, they may actually more than double, or exactly double, or less than double the output they can produce. For example, let's say we take a simple production function, Q equals to the square root of L. Looking at this production function, when we employ 3 units of labor, the firm can produce at most square root of 3, which is approximately 1.73 units of output. Suppose that we double the inputs that the firm uses, so the firm is now employing 6 units of labor. Substituting this into our production function, we realize that the firm can produce Q equals to the square root of 6, which is approximately 2.45, and 2.45 is smaller than 2 times 1.73, that is 3.46, right? So this is saying that when we double the input, with the firm that has this production function can less than double the output. In this case, the firm is, so we would believe that it is not efficient to have a large firm, but probably more efficient to have several small firms. And in this case, the firm has a decreasing return to scale. All right. And to define the return to scale more formally, for any given production function, we can find a parameter lambda that is larger than 1, and we can calculate the following ratio. So I call this ratio m, so we can calculate m, which is if we multiply all of our inputs by lambda times how much we can produce, and we divide it by lambda times the output we can produce before we scaling up our inputs. So if this ratio is larger than 1, we have increasing return to scale. If this ratio is equal to 1, we have constant return to scale. And when this ratio is smaller than 1, we have decreasing return to scale. So obviously, when we have increasing return to scale, it is more efficient to have a larger firm than several small firms. If it has decreasing return to scale, it would be more efficient to have several smaller firms than to have a single large firm. And if the production function has constant return to scale, then whether we have a large firm or we have several smaller firms are going to be the same. And this may seem quite abstract at this moment. So when we solve the firm's cost minimization problem, I'm going to show you an example of what exactly this means, or what exactly the difference will be, all right? And that is going to be next week. So we can calculate the return to scale for the 3 special types of production functions that we have. If we have a Cobb-Douglas production function, we can calculate this ratio m. So we can substitute lambda times L and lambda times K into our production function. We so we substitute those two into here, and we can expand and we can simplify our expression. So we see that on the numerator, there is a times L to the power of alpha times k to the power of beta, and that's also on the denominator. So those two terms will cancel out. What remains is lambda to the power of alpha times lambda to the power of beta divided by lambda. And this is nothing but lambda to the power of alpha plus beta minus 1, all right? So for a general Cobb-Douglas projection function, this M ratio equals to this expression. And as we defined in the previous slide, it is the relationship between M and 1, whether it is larger than, equal to, or smaller than 1, that determines if the firm has increasing, constant, or decreasing return to scale. And here, this relationship depends on the value of alpha and beta, of course. So we have two parameters here. Let's look at a simpler case. Let's say we define the function fx as lambda to the power of x. And we are looking at lambda that is larger than 1, right? So let's just say lambda equals to 2 for example. And the conclusion is going to hold for any lambda that is larger than 1. So in the next slide, I'm going to draw this fx function. So we are drawing the fx function that is equal to lambda to the power of x, and we are picking a value of lambda to be 2. So we are looking at what happens if we double our inputs, all right? But I was saying that the conclusions are going to hold for any lambda that is larger than 1. So if I've listed a few of the values that this function takes when we have different values of x. And I'm going to draw this on the graph. So on the horizontal axis is our x. And on the vertical axis is our fx. Now, if I plot the points that I have here, let's say this is 1, this is 1, this is 2, this is -1, and this is -2. So I have 1, 1, 2, -1, and -2, all right? So when x equals to -2, fx equals to 2 to the power of -2. That is 0.25. So it is somewhere here. When x equals to -1, fx is -0.5. That is somewhere here. And when x equals to 0, fx is 2 to the power of 0. That is 1. All right. When x equals to 1, fx equals to 2. That is probably somewhere here. And lastly, when x equals to 2, fx is 4. So this is 1, 2, 3, and 4 is here. So fx is 0.2 and 4 is here. So connecting all those points, the graph of this fx function will look something like this. It is a convex function that becomes steeper and steeper as x becomes larger. And more importantly, we can see that fx is larger than 1 if and only if x is larger than 0, right? And fx is smaller than 1 if and only if x is less than 0. We can draw those conclusions after we draw this graph. So, and recall, x is our alpha plus beta minus 1, because we define fx as lambda to the power of x, and we put a specific lambda as an example, but the graph will look similar for all lambda that is larger than 1. It will be different if lambda is smaller than 1 actually, but because we are defining the m for lambda larger than 1, we are okay. So this fx, or this m, equals to lambda to the power of alpha plus beta minus 1 is going to be larger than 1 only when the exponent, or only when the x, or only when the alpha plus beta minus 1 is larger than 0. That corresponds to the case when alpha plus beta is larger than 1. And when alpha plus beta is larger than 1, the m is larger than 1, and this Cobb-Douglas projection function has increasing return to scale. And similarly, it has constant return to scale when alpha plus beta equals to 1, and it has decreasing return to scale when alpha plus beta is smaller than 1. So now, if the projection function is q equals to the square root of L times k, for example, the one we briefly used as an example previously, this can be actually written as q equals L to the power of 1/2 times k to the power of 1/2, right? And in this case, alpha equals to 1/2, beta equals to 1/2, and alpha plus beta actually equals to 1. So this is an example projection function that has constant return to scale, that is Cobb-Douglas. So here, if q equals to L times k, for example, then it is effectively L to the power of 1 and k to the power of 1. Alpha equals to 1, well, alpha equals to beta equals to 1, and alpha plus beta equals to 2. And this is a case of increasing return to scale, all right? So here, I'm not sure why equals to 1 is missing. Alpha plus beta equals to 1. And of course, you can have other values of alpha and beta that the projection function exhibits decreasing return to scale. So all those are possible for the case of Cobb-Douglas projection function. It all depends on the value of the alpha and beta. Now, if we have a linear projection function, and that takes the form q equals to a times L plus b times k, we can do the same exercise by substituting lambda times L and lambda times k into our projection function. Now this time, regardless of the value of a and b, we will realize that the ratio m equals to 1. So the linear projection function will always exhibit constant return to scale. It does not depend on the value of a and b. Lastly, the fixed proportion projection function also exhibits constant return to scale. So similarly, if we multiply both arguments by lambda, then the minimum of the two arguments will also be multiplied by lambda. And this ratio is exactly 1, all right? So the fixed proportion projection function also exhibits constant return to scale. So since we did the midterm exam on Monday, for this week, we will only have one extra credit question because we were supposed to have only one lecture anyway. So this extra credit question, you can, same as before, provide your answer on iLearn. Let's say we have a projection function that is q equals to 2 times L squared plus k squared. And we want to determine if this projection function exhibits increasing return to scale, constant return to scale, or decreasing return to scale, or if the conclusion depends on the value of L and K that we are looking at. So you can employ the technique or the method we described before to figure out. So lastly, let me summarize what we did in today's lecture. So we described the production process, and the technology is the ability that the firms have, or the level of or how effectively can the firms produce. We use production functions to represent technologies. We define the marginal product in case of a single input or two inputs. It is the derivative or the partial derivative of the total production function. We introduced the law of diminishing marginal product, which is similar to the law of diminishing marginal utility. We defined isoquant as the curve that contains all the combinations of inputs that can produce the same level of output. This corresponds to the concept of indifference curves in the consumer theory. We introduced the marginal rate of technical substitution, and this is the slope of the isoquants. We also introduced the law of diminishing MRTS. Lastly, we introduced the concept of return to scale, which we didn't define in the consumer theory. We derived, or we calculated, that for Cobb-Douglas production function, the return to scale actually depends on whether the sum of the two exponents, alpha and beta, is larger than, equal to, or smaller than 1. When the sum is larger than 1, the production function has increasing return to scale. When the sum equals to 1, the production function has constant return to scale. And when the sum is smaller than 1, the production function has decreasing return to scale. For the linear production function and the fixed proportion production function, both of them exhibit constant return to scale, and it does not depend on the parameter in those two production functions.